So welcome, everybody. And today, what we're going to be discussing are shared memory parallelization using tasks and Workstream. And the main objective of this module is to identify part of the codes which can be parallelized and that are actually easily parallelizable, and how to parallelize those using either threads, tasks, or a class that is created in DL2 that is dedicated to parallelizations using threaded building blocks for things which are very similar to what happens usually in finite element methods. Okay, so everything that I'm going to say today is being taken by some of the tutorials. So step 9, step 13, the two videos which are number 39 and number 40 of slides by Wolfgang Banger. These are very instructive videos, so if you want to learn more about this. And this page is the most fundamental page for shared memory realization in DL2. And this is basically, I'm going to be discussing what's written on this page, basically, and we're going to be implementing everything that is written in the slides in the Poisson solver. So you have access, if you go to the GitHub page, to the laboratory number 7. And if you download that, this is going to be the starter code for your exercise today. So it contains the solution basically to what we did on laboratory number 6 and a lot of exercises for next week. Okay, so the most difficult part that is going to be the Workstream part is going to be the end point of this lecture, and I'm going to try to convince you that this is the way. There are a lot of things which are not easy when you have to do parallelization. You have to take into account, and I'll try to point out what these things are while we try to parallelize our assemble routine, and we will use Workstream to do precisely this. Okay, so consider the following example. So in the code that we have in the actual implementation of the Poisson problem, this is no longer valid because the sparsity pattern uses the constraints in some sense. So this is not entirely true unless you don't want to use constraints in the sparsity pattern. But in general, once you have distributed the DOFs, you can actually execute number 1, 2, and 3 in parallel without having any bad consequences. So in other words, whenever you can reorder things, that means that without consequences for the final code, that means that the things that you ordered can be executed in parallel. And why do we want to execute things in parallel? Well, of course, we want to execute things in parallel because modern CPUs are very often made of more than one single core. So you have at your disposal, for example, on this computer, I have 8 cores and 16, which are seen by the operating system as 16 cores, so 8 cores with hyperthreading enabled. And of course, once you have this guys over here, what you would like to do is you would like to identify, first of all, what are the most expensive parts of the code. So this is going to be the first part that we want to do. And after you've identified what are the most expensive parts of the code, you want to try to make those run as fast as possible, possibly by parallelizing things, so by making things run at the same time on all available cores that you have. So this is an advanced topic. It's an advanced lecture in terms of finite element methods. So we're not going to be introducing any new topics in terms of finite elements. So we take a break for that, and we start again with new topics on next week. But I want you to be able to run things efficiently from this week on, basically. So from this week on, we're going to be using a lot of very complex tools, and we will be able to solve complex problems with ease, exploiting modern computational tools. Okay, so the next obvious thing that is parallelizable is the assemble system. So for example, the assemble system class that we have basically loops over all cell and does things about the cell. So for example, it initializes the finite element values and assemble the local contribution and then copies this local contribution into global matrix. In principle, besides the copy and besides a numerical round-off and numerical errors that you get because the sums are not interchangeable between themselves, the way that you can do this is by just doing this in parallel for different cells. So you can reorder the cells and that nothing should change in principle. Of course, copying things and summing things into global contributions may give different results if you do things in different order. So just keep this in mind for a second. And we will try to identify ways to parallelize these things, which are fundamentally different with respect to what we had here. So for here, for example, we have 3 tasks, or maybe 4, maybe 5, say in the order of 10 tasks. And this order of 10 tasks you can do in parallel by basically spawning different threads. So making sure that each one of the CPU on your computer does one of these tasks separately. Well, here we don't have on the order of 10 tasks, we have on the order of million cells. So in a certain sense, we have to be careful about what we do, because we don't want to all of a sudden ask to our computer to do a million things in parallel, because that's not going to be very efficient. So you want to keep doing a number of things in parallel, which is compatible to the number of processors, and you want to be able to show, you want to make sure that the actual result at the end is the same. So what we're going to be looking at is ways to parallelize these parts in an efficient manner and to maintain the result identical to what would have been done if you did things in serial. So this is the goal for today. Of course, the thing that is problematic here is that the computations that you do locally, so this part here, which is the symbol local contribution, can be done in serial, in parallel. So everyone can do its own contribution, its own computation on every single cell. So you can split this for all cells that you have. But the copy that you have here is, in general, not something you can do in parallel. So reading is something that you can do in parallel, but writing is not. And the reason why writing is not something you can do in parallel, because access to the memory has to be restricted, has to be done in a precise way. So say, for example, you're accessing index I, and all of a sudden processor number 10 tells you that you have to access to write into index J instead of index I. And you don't want these two things to mix together, because otherwise you might be having things that happen to end up in the wrong position instead of doing things in the correct time. So this part is usually a serial part, but it's a very cheap part. So it's not expensive to do this. It's as fast as the bus speed that you have in your memory. So how do we do this in the shared memory model? So what is a shared memory model? So if you think about the shared memory model, then what you should be having in mind as a picture is the following picture. So there's a block of memory, which is the main memory of the computer, which is shared for all the CPUs of your computer. So think about these threads as being different CPUs, and being different CPUs that have access to the same memory. So you can read and write on the memory at the same time if you know what you're doing about writing on different portions of memory, but you cannot read and write on the same memory at the same time. You have to make sure that when you write in the memory, you just do this single threaded, so only one thread per moment, for any single moment writes in a given part of the memory. However, everyone can actually access the memory and read the memory at the same time. And of course, you also have the possibility to have private objects that are particularly used by single threads, by single CPUs, which are not seen by any of the other CPUs, and each one has its own copy of these things. And of course, this may be convenient if you have, for example, to initialize certain so for example, for local contributions, you want to initialize local finite element values and finite element gradients. And of course, you don't want the finite element values and gradients on a given cell to be modified by somebody that thinks that you're living on a different cell. So you have to be careful about how you do these things. But in practice, this can be done by splitting the memory into a sets of a private shared memory, of which every single process knows to what it has access to, and a global shared memory that allows you to, for example, share the entire triangulation and share the entire offender and so forth. So in a certain sense, shared memory models are simple to write, are simple to think about, and are simple to do in an easy manner, simply because you have always access to the same memory. So you don't need to replicate information across CPUs unless strictly necessary, like in this particular case. So The essential part of this is that you are responsible for synchronizing the access and for protecting when, for example, when you're writing inside the memory, and you are responsible for accessing globally shared data and making sure that you're accessing the correct data and not something that somebody else has been writing to. So the way this is done usually is by basically taking something which is a serial task that is here, and that's at some point when you know that you can do some things in parallel. For example, you want to assemble to four different cells. You start spawning different tasks. So basically, you create a copy of the program in memory, and the copy of the program in memory simply runs the same thing on different paths. So you have different paths of executions that just run the same thing. And you can see this by looking at the top program and then seeing when this happens, you see all of a sudden the same number, the same name of the program that appears several times, and then all of a sudden it becomes one again. And these are the so-called the spawn and join part, so in which you spawn a parallel part here, and whenever you have to write, for example, on global memory and write this in a safe way, what you do, you acquire lock. So you say, okay, wait, nobody can write on this part of the memory. You do the writing, and then you release lock, and you let everybody else do the same. So there's a lot of things that you have to keep in mind for these types of things. So we will try to go into details of all of this problems, and we'll try to understand how to construct these guys. So, for example, this is it's very good for a small number of completely independent tasks, which is what we're discussing before. If you have to write onto well, reading is safe, but if you have to write in some part of the data which is shared, you have to lock things, like create a mutex in the language of threads. Mutex means it's mutually exclusive access to memory, and whenever you create a mutex, nobody can actually do anything to the. Nobody can do the same thing that you are doing at that moment at the same time as you are doing. So, for example, you arrive to a point in which you want to write into memory, you create a mutex, and anybody that needs to write into memory sees that there is a mutex active, and it will not write into memory at the same time until you release the mutex. Then somebody else will acquire the mutex, they will write into memory, and then release it afterwards. Okay, so there's a lot of potential for deadlocks, and there's a lot of potential for making things disastrous. So in parallel computations, you have to be very careful. And this is exactly the argument of today's task. So we will try to do this today. So how do we do this in deal 2? And let's start by querying some information. So for example, how do you ask how many cores you have and how many threads you have? Or how do you set the maximum number of threads that you want to have in your code? Well, this is exactly how you do it. So you have a class in deal 2 that is called multi-thread info, and this allows you to query the number of cores or the number of threads, or to set the number of units. Okay, and how do you actually create threads? Well, that's it's a simple way. In C++ 11, it's much simpler than what's written here. You can use the auto keywords, and here we have a class which is called threads, and this class takes an argument. Well, it's a couple of members. One is a new thread member, for example. This is what we're going to be using, and or new task member, and I will be discussing about the difference between a new thread and a new task. The background engine that is used in the deal 2 library today is threaded building blocks from Intel. And we have a unified interface towards threaded building blocks to make life easier and to make it interchangeable with other libraries when you want to change. And in 9.3, we were in the process to switch to a library that is called TaskFlow. And the idea behind these libraries is that spawning a thread is simple, not always the best option to do. And what you would like to be able to do is to spawn, for example, tasks. So to create a list of tasks that you want to execute, and make sure that at any given time, a fixed number of tasks is being executed in parallel. And if you do it this way, then you need to have somebody in the background that is actually responsible for scheduling those tasks, and to actually, picking up a new task and executing it until it's finished, and then giving back the results when that's finished. And all of this is very complicated if you want to do from scratch. And if you use these types of libraries, it's just a matter of creating basically wrapping a function call inside either a lambda or a function call that actually calls on the function, passing the class and the arguments of the function itself. So in this particular case, so for this example, we are creating 3 threads of a function that returns a void, so functions which are void functions. And in principle, what you can do is you can do the same thing with lambda functions. So what you do here, if you do auto t1 equal threads, new thread, and then you call a lambda function that executes something. And if you, as soon as you have written that and the code arrives at this point, what it does, it doesn't stop and waits for the execution of this, but it passes control to the next line, and it executes the next line in parallel with respect to the first line. So that's what happens. So basically, these calls here are non-blocking calls in the sense that as soon as you arrive here, the execution just passes over, and it starts doing this in one of the CPUs, and it gives you control back. So you do not expect, when you see these types of things, what you can expect is that thread number 1, 2, and 3 are run somewhat in parallel, maybe not in this order. So they could be ordered arbitrarily, like 3, 2, 1, or 3, 1, 2, or 1, 3, 2, or whatever, doesn't matter. The essential part here is that if you need to synchronize with some of this, for example, you want to wait for the hanging node constraints to finish because you need, for example, hanging node constraints for something which is later needed, then you can actually wait for thread number 1 before doing something which follows this line. Okay? And this can be done in a very complex manner. And it can be done, for example, by spawning a new thread that waits for thread number 1. And it can be very complicated. It can also be very dangerous because if you, for example, if you spawn something that waits for number 2, and you spawn something that, for example, if you spawn thread 3 that waits for number 2, and then you spawn another thing that, for example, in thread 2 you wait for number 3, then you're going to have a problem because you might end up waiting forever because somebody waits. Both are waiting for something which is not enough. Okay, so this call here is a blocking call. The other option, for example, is to look at the example of assembling the cells. This is the other example that I gave before, and that's a different stuff with respect to this. So let's take a look at this, and let's try to do the same thing. So the simplest idea that one could have is to do exactly the same thing, maybe using a thread group. Okay, and the thread group has a difference that it has a plus equal. Oops, it has a plus equal operator that allows you to attach new threads to this threads group and then wait for all the threads to finish at the same time. So this is equivalent to ask thread 1 join, thread 2 join, thread 3 join, and so on and so forth. And this is equivalent to waiting for all threads that have been added to this thread group and to wait for all of those threads before proceeding with the execution. And here, there is an issue with this type of things, and the main issue that you have here is that if you do this, what's going to happen is that the system is going to spawn a number of threads which is equal to the number of active cells, and this is not very efficient for several reasons. First reason, I mean, of course, you need to have a function that assembles on one single cell, and this function may be expensive to do, but we will see how to make this work in a more efficient way. The essential part here is the following: it's not really possible, it's not really useful to have millions of copies of code that actually execute at the same time. The main reason is that the creation of a new thread and the waiting for the thread has cost, and the cost is a non-negligible cost if you have to do this a million times. It's a cost that is associated to the fact that you have to communicate with the operating system. You have to ask permission for the operating system to access a new processor. And as soon as you have access to the new processor, those things will run in parallel. And then when one of them finishes, it has to again communicate with the operating system and so on and so forth. So creation of new threads is expensive. Joining of new threads is expensive. And if you want to do this, you don't want to do this on every single cell. So you want to do, well, of course, the best way to proceed would be to split the range of iteration that you have here into sub-ranges. And this is exactly the way that typically we do this thing. So we split this on a cell range. So you start with the cell range that is here. And instead of assembling, doing things in parallel for every single cell, what you do things in parallel for every single range. So there's a couple of interesting functions in the threads namespace that are called, for example, split range. Takes the dot handler begin, active dot handler end, and a number of virtual cores in which you want to split these guys, and it returns to you a pair of iterators in which you can run. And now, at this point, you know that you have a set of iterators ranges. So you basically split, say, for example, you have 100 processors, 100 cells, and 10 processors. So you want to go from 0 to 9 on the first processor, from 10 to 19 on the second processor, from 20 to 29 on the third processor, and so on and so forth. And this allows you to do precisely that. And it does so in a balanced way so that you don't have too many differences between the various ranges. Okay. So the thing here is I am doing a number of threads. So I'm spawning explicitly a number of threads, which is equal to the number of virtual cores. Okay. So I'm not spawning a number of threads, which is equal to the number of cells. So I'm just splitting the work that I have to do in fixed amounts or in almost fixed amounts. And I'm just trying to do that and what I'm doing here is I'm proceeding the same thing that I was doing before, but instead of doing it from begin to end, I do just from one piece to another piece. Okay. Of course, again, we have to be careful because in this part over here, inside this code here, there are some parts which are serial. So some parts for which we have to access, we have data races most of the time. So the way to get rid of this, to do this is to make sure that you create a static object, which is shared by all the objects that need to access the system matrix, for example, or the system right-hand side. And once you've created one of those mutex, you make sure, so the fact that you have this static keyword in front here says that you create only one of these objects for all of the guy. And once we acquire the mutex and you start doing all of these things, you are guaranteed that you are the only one that is doing this path. Okay, so this is the way to prevent writing and writing on the same area of memory at the same time. Okay. Of course, this is an issue, and the issue that we have is that we don't want to have a lot of processors waiting for you to write things. So in particular, the principle by which we can prevent data races, the principle by which we can eliminate the bottlenecks that are associated with the fact that everybody has to wait for everybody else, is to split the things into the task concepts. So what is the task concept? Well, there's let me write this. Let me show this picture. It's a picture that I use very often, and I spend a lot of time in trying to explain this part. So this is called the Workstream class in Real 2, and it's one of the there's a paper that has been written by Wolfgang that shows how this can be very efficient and extremely robust for finite element methods. And this has been implemented in the library, and it's available for you to use. And it has the learning curve to learn to use this class, to use this object is a little bit steep, and I'll try to explain to you what is the main idea behind this part. So the idea is there's often you have a lot of things which are extremely expensive to compute, and we call this the red part. So the red part are a expensive task that you want to compute. And think about this yellow block over here to be, for example, the assembly of the local parts of the finite element methods on a single cell. Okay, and so this assembly has to be repeated for every single cell. So for every single cell, you want to assemble the local contribution by computing all the mappings and all the gradients and everything else. And then you want to copy these contributions from the local matrices to the global matrix. And this is exactly how we do this. So we loop in serial, we loop for all cells, and we call this yellow block all of the time in serial. As soon as we're finished with one block yellow, I go to the next block, and so on and so forth. This is inherently serial. And so the way to proceed in order to parallelize this and avoid bottlenecks and avoid also data races is to rely on a scheduler. So what do I mean by relying on a scheduler? Well, the idea is these copy operations need to be done in serial. Right? And so in a certain sense, well, actually not in serial, they can be done in parallel with respect to other things, as long as you're not accessing the same resources. So in a certain sense, the idea is we create two different stacks of tasks and two different pipelines and two different, these objects over here are a first in, first out type or ordered list of tasks. And we make sure that the copy line, and let me call this copy line over here, is executed in serial. That means there is only one CPU that is copying at any given time on the processor. Okay, so the copy line here is filled with the red, with the green data that comes from each one of the cells. And if you need to do this, you need to split the operations in a lot of very complicated things, but you understand how this works in a few slides. So the idea here is to split the part which is expensive from a computational point of view and make a list of all the tasks that you need to do in the expensive part. And as soon as you've finished these expensive operations, you basically transfer the copy objects that you've created in the expensive operation, which I haven't written here, but what happens here, you basically you work on this guy over here. As soon as you finish working on this guy over here, you produce a object that needs to be copied somewhere, and you put it in the copy line. And then you keep going the same thing on a balanced manner with all the CPUs that you have at your disposal. So the task, well, the essential goal that we want to achieve here is we want to be able to perform the most expensive parts of the task as much in parallel as possible without interruptions. So that means we want to have the CPUs working on the red part for as long as possible. And we only want to have one single CPU that works on the green part if necessary. And this is achieved by the task scheduler. And this is the threaded building blocks in the build2 library. So it's a library that allows you to do this type of operations. And it basically lists, it allows you to split the work on these two lines, one that actually is expensive and can be done in parallel without arms, and one which is very cheap but needs to be done in serial. Okay, so the idea is whenever there's a free core, you use it to perform the next task, and all of the sensitive operations are continually executed. So you always have this executed in parallel, and you see here, whenever this list is not empty, CPUs will keep working on this list. And whenever each one of these CPUs has finished working on the red part, it will generate a green part, which is the local matrix and the local right side. And these green parts will be outsourced to a different processor that will copy this on the global line. Okay. So all of these things can be done independently. And of course, in order to do this independently, you need to have two different data types and two different objects. One that allows you to create temporary objects for the primary functions, and one that allows you to create temporary objects where you store things that you need to copy globally. And this is exactly what's going to happen in the assembly. So let's take a look at where this can be identified in our code that you are so familiar with now, by far. Okay, so this is the example of assembling finite elements on a single cell. So let's say that what we do here is simply create the same function that we have in our system, in our assemble system, and we just replicate it, and we loop over all cells and call this assemble on one cell function. Okay? This can be done very easy. And we will see whether this is effective or not and how expensive this is. And then we will try to reduce the cost of this. So this is exactly how we will start. So we will create an object that assemble on a single cell, and we will call it on every single cell. Okay. Now let's take a look at these guys over here. So these guys over here, there's one expensive constructor call. So this constructor call here initializes a lot of stuff and tries to build a lot of stuff which is extremely expensive to build if you do this for every single cell. So you don't want to have one of this guy around per cell. You want to have one of this guy around per parallel task. So every single task that is running in parallel needs to have its own FE values because it needs to initialize this for its own cell. But you don't need to have one of this per cell, but only one of this per task, per parallel task. So the number of tasks, the number of objects that you want to, the number of times you want to reinitialize these guys is to create a new object of this guy is just equal to the number of parallel tasks, not equal to the number of cells. Otherwise, it's going to be too expensive. We will see this in a moment. Okay, so the repeated memory allocation that you have here also doesn't need to be created every time. So you need to have a number of these guys, which is equal to the maximum number of objects in the lines that you are putting in the, so let me show here, the maximum number of objects that you need in this copy line, of course. And this is going to be equal to this number over here times a factor, which is something that we will be discussing about in a few seconds. And after you have done these two things, so these two parts of it over here will be living in two different objects. One in the per task data and one is a per data, is a per operation data in a certain sense. This task here is independent, so you can execute this once you have these guys over here. You can fill those guys totally independently. While the last part that you see here is the serial part, serial operation. So we want to outsource these 1, 2, 3, and 4 objects to 4 different things. And then we will see exactly how these actually work. So the idea in the library is to use an object for these guys for everything that is expensive and that is used as a scratch that is needed for the computation that are expensive here, is to use a object or an assistant structure or class that is called scratch data that contains all the reused data structures. So for example, FE values objects or Apple vectors and storage containers, or everything that has to be pre-computed. Right? This object needs to have a copy constructor, okay? And some of those need to be manually constructed, and only one initial instance of this class is constructed at the beginning, while threaded building blocks duplicate this as needed. And the maximum number of duplication that is done in threaded building blocks is equal to an argument of functions that we will say later on, and it's called Q length. Okay. Okay. So the scratch data here contains right-hand side values. For example, the finite element, the quadrature, the flags, and all of these are basically required for you to use FE values. We will use a drop-in replacement. There is a scratch data, default scratch data in the DX library that can be used for this type of thing. So you don't need to remember everything or to make sure that this is constructible. We will replace basically the FE values that we have in the code using the scratch data that is created in the library. Okay, good. Once you have that, the per task data, this object here, it's an object that is created for every task. And it basically contains all of the data structures that are required for the serial operation. So the maximum number of this guy is Q length times chunk size. And you make a lot of these copies, okay? This has to be self-contained. And it has contained, for example, the cell matrix, the cell right-hand side, the degrees of freedom indices. And all of these guys are the ones that are filled inside the expensive part, and then they are outsourced and sent to a queue that is in charge of copying this to the global matrix. Okay, so this is used in 2 places. In one place, you write on these things, and on the other place, you read on these things. So on the first place, which is where you write on this, is basically where you actually do the computation of whatever needs to be copied somewhere. And in the serial functions instead, this is just used as a data out object. So it's something that it's used just to read. Okay, so if you look at this, the way to use this using Workstream, it's exactly the same as before, but instead of reinitializing things in the way that we did, that we usually do without these 2 objects, we basically use the FE values readme cell that comes from scratch, and you assemble one cell. Instead of just taking the cell, it takes also a scratch data if it has. So basically, we outsource the initialization of the scratch data, the creation of the scratch data, the FE values creation, which is exactly what would happen in the serial case. In the serial case, you create the scratch data outside, and here you have to create the scratch data outside, but a number of times, which is equal to the number of ranges in which you want to do things, the number of cells in which you want to do things. Okay. And as soon as you've created that part, the data that you want to fill is no longer just a cell matrix and cell right hand side, but it's the, so it's not just cell matrix and cell right hand side, but it's data dot cell matrix and data dot cell right hand side. And the data is passed to you as a read-write object when you assemble one cell. Okay, so you write on top of this and then you go forward. And as soon as you finish this, the assemble is not finished. You still need to copy the local data to the global data. And you can do this using, for example, constraint distribute local to global. This is exactly the way that we will do it in our code. And this simply takes the data that you've computed previously and it copies to global data. Okay. So you write this writes feeds data on the first class data to the single class object, which is called system matrix or whatever else you need to do that. And it is a serial operation. Okay. Now let's try to use those guys in serial. So if you had those guys in serials, the way that this would work would be to simply have the scratch data and the task data, and then loop for all cells and assemble system on one cell, passing the cell, the scratch data and the task data, and then copy local to global. So basically, we split the copy and the computation into two parts. And this splitting of the copy and the computation into two parts with data objects that are the minimal data objects to do this allows you to use very complex task scheduling and to guarantee that the results that you get at the end is unique. And so now if you look at this thing over here, that doesn't look so harmful and so difficult. The main difficulty here is to understand why you need to structure data in this way and why you need to do this way. And this is, I hope you got the main principle, the main message behind this. Once you have these guys, you can actually execute this in parallel very efficiently using the class that is called Workstream. And Workstream takes all of these objects as arguments. So it takes a scratch data and a pre-task data, a range of iterators on which you want to use these guys, which you need to compute those guys. And it needs to have two functions. One is the assembly function and one is the copy function, and the scratch data object and the task data object. Okay, so it takes a range of objects on which you want to work. This particular case, it uses the class method. So this says, okay, I'm using an instantiation of a class and then member functions of the class, but there's also methods that allow you to just call here a lambda function that takes a symbol system of one cell or a copy local to global here. And if you look at this, the way that this actually runs has a very important feature. And the very important feature is that the result that you obtain with this run is identical to the serial run, also in terms of errors, of round-off errors, because this object run guarantees that the copy local to global is done in the same order of the iterator ranges that's done here. So basically, by using this guy, you are offloading work and copy in as parallel ways as possible, and you're guaranteeing that the copy is done in serial, always in the same order. So the result that you get is identical to the serial case. Okay, so we will do this, and we will try to do this. And the main documentation for this is in the Workstream namespace. And keep in mind that if your objects are very large or the constructor is expensive, you have Q-length copies of the scratch data and Q-length times chunk size copies of the copy data in general. And this is the documentation of the Workstream that we'll take a look at. Okay, so let me stop the sharing for this, and let me open up the Visual Studio Code. And actually, before I open up Visual Studio Code, I'll copy here the GitHub invitation code in the chat for you guys. So this is the starting code that you can play with and you can follow up. Okay, so let me see if you have not accepted. No, nobody's accepted the assignment yet. Okay, so if you click on that, you can follow live. Otherwise, we will do this as usual on my desktop. Okay, let's take a look at the code that I've created so far. So this is the Readme file. And the Readme file contains a couple of things. So the first thing that I ask here is to instrument the Poisson solver with the timer output class. This is the first task that we want to have. And the reason why we want to have this is because I want you to be very aware of what is expensive to do in the library and what is not expensive to do. First thing that you need to do before you start optimizing anything is to check what needs to be optimized. It doesn't make any sense to try to make a function that takes 2% of the total time faster. You want to make sure that the function that takes 80% of the total time runs faster, not the one that takes the smallest time. Okay, so the first thing that I ask you is to instrument the Poisson solver and try to figure out what are the functions that actually take a long time. Okay, and then I want to be able to control the number of threads. So I want to be able to add a new parameter that I will call maximum number of threads that calls multi-threading for set thread limit in the given argument. And then we start by basically doing what we had done in the class, in the slides that I've shown in the class. So I will start by first trying to run in parallel some of the things that are there. And then I will try to use split range in the assembly system and on whatever seems to be expensive to compute. We will be using the scratch data and the default copy data that comes from the library DL2. So we don't need to have a full objects of this guys. We don't need to have different, to create different objects for this. We just use what is already available in the library. Okay, so let's start with the first task. And the first task is to instrument our Poisson solver with the timer output class. Okay, so here I add the timer output class. So this is in DL2 Doxygen timer output. So this is in base timer here. And I create an object of timer output, which is this guy. And I create it as a first thing, timer output timer. Okay. This object needs to be initialized when I construct it as here using the documentation of the library. This needs to have a stream on which it wants to output information. So we use stdcout here. And output frequency here needs to be for example, every call summary, every call and summary, or never. And so what I'm doing here, I will just do summary of the output data. So this output will be generated only at the end. So I take output frequency. And this is going to be timer output summary. And then I'm going to do this timer output CPU and wall times. Okay, so now I've created a timer, and this timer is going to be outputting summary at the end of the execution. So when it's destroyed, and it will output on standard cout and will output CPU and wall time information. Okay. In order to trigger the timer to actually count what is happening, what we will be using is the scoped timer, which is usually created using this guy over here. Timer output scope, timer section, and this is the type of things that we want to have. Okay, so we are going to instrument each one of our calls. For example, the make grid call, we are going to create a scoped timer, which is called make grid here. And for each one of the methods that we call, so for each one of these functions, we will do this. So this is going to be the constructor. Let's see which one of these guys takes longer. Then this is the initialization. So the way this works is you create these objects. This will start the timer, and then when the object is destroyed, so at the end of the scope, this will stop the timer and store in the section initialized how many times you've called it and what is the total execution time of that call. Okay. Then we have the same thing, but this is going to be called pass string. Make read already did, and refine read. Setup system. And assemble system. Solve. If you notice in the starter code, I added another option. So if I have Trilinos installed, I will use algebraic multigrid as a precondition. This is an optimal precondition of these problems. If you don't have Trilinos installed, it will keep using precondition identity. And I am using a global solver control, which is initialized inside the, let me show this before I keep going. I'm adding details to this guy slowly, and I'm making this as complex as it can be. So I'm taking a parameter acceptor proxy of the reduction control guy. Reduction control is the type of control that we're using, and it's called solver control. And it's the same thing as the solver control that we were using before, but it allows you also to specify just how much you want your tolerance to drop before calling the day. And it allows you to control things in two ways, either as a absolute control or a relative control, while the other one was just absolute control, absolute error tolerance. And this parameter acceptor proxy uses parameter acceptor for reduction control as well. So you don't need to do anything by hand. It will define the parameters for you in the correct manner. So take a look at the documentation of parameter acceptor proxy if you want to understand how this works. So it basically exploits the solver control, parse parameters and declare parameters functions in order to create the correct sections in the parameter file. Okay, so we have solve here, and then we have estimate, and we have mark. And we have output results. So if you look at the output results now, I'm also outputting the exact solution, the interpolated exact solution, and I'm also outputting the error estimator to give you an idea of how things are done. And I am using a mapping, which is a curved mapping, possibly, that uses the mapping degree as the output. Okay. Print system info, I don't need to check, and then the run is going to call these guys, all of these guys, all of these guys in here. Okay, so if you now build this and run, for example, the last test that I asked you to run. So let me show you the parameter file for this test. So the parameter file for this test contains as an exact solution equation minus x squared minus y squared plus 1. And it's computed on a hyperbole centered in 0 with radius 1. So this is going to be 0 on the boundary. And I use 0 Dirichlet boundary conditions there with finite element degree 1 and mapping degree 1. And I'm using a number of global refinement 0 and number of refinement cycles equal to 6. And I'm not using a direct solver, but I'm using the preconditioned algebraic multigrid method with conjugate gradient. Okay. If I now run this, it should have built everything. timer output scope. And we want this timer output to be mutable. So the reason why it was complaining is because the output result is marked as const. So it's not supposed to be modifying member functions, member objects of the Poisson class. So I'm making the timer output a mutable object so that it can be modified inside const members. Okay. This is now linked the Poisson executable. So if I now run Poisson with test FEM, it blows up in my face. Oh, yes, of course. And the reason why it's doing that is because I already started doing experiments with what we had. Okay. Okay, so now I'm running the Poisson test. You'll get a output result that tells you what is the L2 norm of the function, the L infinity norm of the function, the H1 semi-norm of the error. And here we also get the estimator. So if you take a look at the test.prm that we're using here, this test.prm is using as an estimator the residual-based estimator that we constructed all the time. And it's computing the L2 norm, L infinity, and H1 semi-norm. I don't need more L infinity. I don't want to use those. And it's computing the reduction rate log 2 of the degrees of freedom. So you see this will only work in dimension 2, unfortunately. There's a bug in the library that does not allow you to get the correct rates in dimension 3, because it does not take into account the fact that this has to be, you have to use a different power when you have dimension equal to 3. But you see in dimension 2, you see convergence of order 1 in the H1 semi-norm L, convergence of order 2 in the L2 norm of the error, and the estimator converges with order 1, and it is strictly larger than the H1 semi-norm error, which is the error that you were expecting to get this. And the global objects that you have at the end tells you what's the total CPU time and the total wall clock time that has elapsed since the start of your code. And before I run things, I ask to the guy to, in the main file, I also asked the guy to actually output some information. And the information that I ask to the guy is written into the run parameter. So if I go to the run method, there's a print system info here. And this print system info return the number of cores and the number of threads before returning, of course, the number of cells that are generated on the gate. So if you look at the full run, it says to me that the number of cores that I have in the code in my computer at the moment is 16, and the number of threads is actually 16. And then I start with the execution of all of these guys. Okay. So this is running using algebraic multigrid as a preconditioner, as I showed you in the solve method, which is here, because I have Trilinos installed. And as you see, the number of the, one thing about the algebraic multigrid method is that the number of convergence steps is very small, right? So convergence of the gradient converge in 1, 2, or 3 steps at the same time. Okay. And at the moment, I'm doing this with the global multi-strategy. If you want to see the output of this, I can show them to you in ParaView. So this is the solution. I go to 0. And of course, this doesn't look like a ball in the first iteration. And it doesn't look like a good solution, of course, because there's not enough degrees of freedom associated with this. But as soon as you go to a little bit larger number of degrees of freedom, you see that you expect the solution, the maximum of the solution, to be equal to 1. And this goes quickly to that maximum value, which is 9.7, 10 to the minus 1. And this is with order 1 finite element and mappings. So the degrees of freedom, the usually boundary condition is set up on the boundary to be 0, and you have an error that is approximate, that is coming from the grid. So one of the things that I asked you to do last time was to explore what was happening if you changed the mapping and the finite element degree. And now let me show you what happens if you do that. So for example, if I use a second order finite element degree, actually a second order mapping and a first order finite element degree, take a look at the errors that you have here. Actually, let me copy those errors onto this file here. Maybe without the rates, which I don't want to have. And now here I should have, this is 0, 1, 2, 3, 4, and 5. That's the estimator. And if I plot also the error and the L2 error and the H1 error, you will see different type of inclination of this thing. So the error estimator is here. The L2, L infinity errors are, that's L2, L infinity, and H1 seminar. Let me not compute the rates. So we're going to copy this as it is. We cells those L2 and H1. So this will be x equal 1, 2, 3, 4, and 5. So I want to have not 2, but 3, 4, and 5. And this should be L2, H1, and error estimator. Not table number 5. 1, 2. Zero, 1, 2, 3, 4. Sorry, I had to start from 0. Clearly. Okay. So as you see, the error estimator is the one that is on top, and it has the same same inclination of the H1 error, which is the red one, might have just shifted on the top. So there's a constant in front with respect to the 2. And the L2 error instead goes down with a higher inclination. So this one goes down with the order 0.5 with respect to the DOFs. So remember, this is minus R over D. So if d is equal to 2, this is r over 2, and r is 1 for this guy and 2 for this guy. Okay. And now I want to see what happens instead if I choose mapping degree equal 1 and run again the test. You should see exactly the same type of rates with a difference, and the difference is simply that the difference that you will see is that the error is much larger with respect to this one. So let me just create a new table. So I should see the estimator is roughly identical, but you have a larger error with respect to the other two norm because it's shifted on top with respect to the other one. The H1 semi-norm doesn't seem to be so bad in this particular case. Now, let's try to see what happens on the other options. So if I have finite element degree equal to 2 and mapping degree equal to 1, and here is where things start to become interesting. So in this particular case, if you don't have the correct mapping and the correct finite element space, you shouldn't be seeing the correct order of convergence. So let me, for a moment, run this again with the rates written in the table so that you can actually appreciate the rates computed by that. And as you see, instead of computing an error estimator in order 2, which is what we would expect in the H1 semi-norm, it computes an error estimator of order 1.5. So this is with finite element degree equal to 2. And I would have expected H1 semi-norm to be equal to 2 in order, and the estimator to be equal to 2 in order. And the L2 norm should be 3. And instead of having 3, 2, 2, we get 2, 1.5, 1.5. And the reason is why is that we are not using the correct finite element mapping degree to describe the boundary. And if you look at the picture that I'm showing here, this is going to be something which is, this is quadratic, of course. If I have the work by scalar, this is a quadratic representation of my function, and the work by scalar, of course, doesn't need to be done on the estimator but on the solution. And as you see, I have a quadratic function here, but the boundary is terrible. So I'm not representing the boundary correctly. And even if I go forward, this is better than before, but the boundary is not represented correctly. So the geometry is wrong. And if you get the geometry wrong with these kinks, you lose half an order of convergence. If you want to maintain the same order of convergence into finite element space, what you need to do is you need to maintain a matching order of the finite element space with respect to the mapping degree. Okay. So here, if you put 2, what you will see is you should recover the correct order of convergence. And in fact, we do even better. So in this particular case, we see 3.2 and 3.2 here, and 4 instead of seeing 3 and 2. So this is just because the problem is symmetric with respect to 4th order. So there's a lot of symmetries in there. So you see something which is better what you would expect. If you now plot this and look at the way this looks like, even at solution equals 0, this is much, much better. Even with just 4 cells, you get 9.9, 10 to the minus 1. And the errors that you see here are 10 to the minus 8 at the end. So this is very, very low, for very little number of degrees of freedom. This is converging very well. Okay, so this is what you would see here. Okay. So let's go here. And now let's try to understand what are the bottleneck of our problem. So if you look at the bottlenecks of our problem, 49% of the time is spent in the assemble system. 30% of the time is spent in the estimate of the error convergence rates. And 10% of the time is spent on the output of the results. If we try to do setup system, that's 2.4, or solve, it's 10% here, 7.9%. And the reason why it's 7.9% because I'm using algebraic multigrades. Otherwise, it would be much larger with respect to what you see here. But if you really want to tackle something and to improve the speed of your code, you want to make sure that you go and try to make the assemble system faster. Okay, so let's copy this and let's now change the parameter file. And let's try to make this run faster by just doing trivial parallelization. So let's touch parallel.md. Let's call this parallel.md. And let's open this guy. And let's copy here the results before parallelizations. Okay, so before parallelization, and just to make sure, we also copy the test file that has been used. So we copy the last used parameters. And we go here using as parameters this. Okay, so we have a log of what we have done so far before parallelization. We would like to see these numbers go down. Okay, now the total seconds, number of seconds that is here is a very small number. So in order to see some improvements, I would suggest that we actually use a larger number of refinement cycles. So let's say we use 9 refinement cycles here. This should go for a much longer time. And let's say that we use 9 here. And he's running with finite element degree 2 and mapping degree 2. This will take a little longer. So in the meantime, let's add the control on the thread building blocks, on the threads that I was asking in the code at the beginning. So in order to do that, we make in Poisson.h, we add a parameter, which is called here int number of threads. And by default, we set this to equal to -1. And we add a parameter here, which is number of threads. Here. When we set up the system, we actually, when we print the system information, we make sure that this is actually called, we actually set up the number of threads to something which is reasonable, which is here. Before actually outputting the system information, we make sure that if number of threads is different from -1, what we do is actually we also make sure that this is greater than 0. And then we call multi-thread info set thread limits to number of threads. And this expect an unsigned int. So we static cast it to an unsigned int to make sure that we don't get errors at compile time. And we can do that simply because the number of threads is strictly greater than 0, and we check that this is actually the case. Okay. Now, I think 9 was a little bit too much. Let's make, instead of 9, 7. It should take a little longer than before, but not too much longer. A few seconds. I wanted to see something above 10 seconds. Okay, and now we copy these two guys, both wall clock and CPU time. Okay, so we want to go. Now we arrived to 30 seconds in terms of CPU time, 24 seconds in terms of wall clock time. The reason why this number is more with respect to that is because most of the library internally is already multi-threaded. So a lot of the things that are happening in are already multi-threaded. And as you will see, now if I build and run, I can actually set the number of threads to something which is equal to -1 here. So this was achieved with the default number of threads, which is -1. If you have questions, stop me, okay? I want to make sure that we get on the same page, that we are on the same page here. Okay. This seems to have compiled. So Poisson Test PRM. I don't want to wait so much while we test. So while we test, I just do 5. Okay. And I should see here, number of cores 16, and number of threads 16. And if I copy last use parameters to test PRM, I should see also now a number of threads equal to -1. If I set this number of threads to 1, I should see a wall clock time which is larger and should be close to the CPU time. Exactly. As you see, now the CPU time is 1.37 and the wall clock time is 1.39. And I should see here, number of cores 16, number of used threads 1. So what this is telling you is that some of the calls of the library are already multi-threaded. So you were saving a little small percentage of work in some of these function calls. So for example, on the estimator, you have some 32% here, while here is 25%, which means that internally that is already parallelized. Okay. Still, the assemble system, which is what we wrote, is not parallel. There's 56% here and 46% here in the assemble system. And the reason why you see this large number is because the initialization of the FE values is allowed to be multi-threaded in that, and the distribute local to global tries to be multi-threaded whenever possible. So everything that can be parallelized in the library has already been parallelized. But as you see here, the total number of seconds of these guys are almost identical. So we have to work on the part which is the most expensive part, which in this particular case is the assemble system. Okay, so how do we do that? Well, let's start by considering the fact that we can exploit the, basically we can use assembly on subranges. Okay, so we will make this in the following manner. And we create a function in the Poisson.h file, which is called void assemble system on range. And this will use a const of handler dim active cell iterator and begin and here. Okay. I created a function that allows you to assemble the system on the range. And I basically want to transform the current assemble system into an assemble system on range and split this assembly on the different ranges. Okay. And then I would like to do this in parallel and see whether we get something which is better or worse with respect to what we see now. Let me just copy this as well, because we might see slightly different numbers at the end of this run. So I want to make sure that we are conforming with what we see. Okay. So how do we assemble system on range? Let's look at the way that this is currently done. So assemble system at the moment is basically initializing a lot of stuff at the beginning and then looping over the cells. We can do exactly the same, and this is exactly what I want to do. I want to copy this for the moment as it is, but I want to pass to this function, assemble system on range. I want to pass both begin and end iterator. And since I want to be looping over begin and end, and I want to use just begin. Okay. So what I would like to do here, actually, I like it better with the const, sorry. What I would like to do here is, instead of doing const to cell, defender active cell iterators, I want to do for auto cell equal begin cell different from end plus cell. So I just want to do this on each one of these guys. Okay. And the end cell is given by the argument of the assembly system on range. Okay. Now, everything else is exactly identical. So here I'm just assembling the system on range. And if I pass the defender begin active and defender end, they should work out of the box. Okay. So let's, the only thing that is important here is that this distribute local to global needs to be guarded in terms of a mutex, with a mutex. Okay. So it needs to be guarded with a mutex. And in order to do that, we do static threads mutex and as you will see here, and there will be a namespace with threads and mutex, which is this guy. And it's basically derived from my standard wildcard. It's exactly the same thing. So I take this mutex and is the assemble mutex. And when I'm here, I want to make sure that the assemble mutex is required. And when I finished, I want this to be released. An alternative way would be to do scoped mutex. But we're not doing this now. Okay. I'm not calling this yet anywhere. I just want to make sure. So this too should go after constant name, saying in the code. Questions so far? Okay, sorry, lock. It's now called lock and unlock, sorry. Lock and unlock. Okay. Now, the assemble system that I see here, if I want to have this in serial, I can simply call assemble system on range using dot handler begin active and dot handler end. So this is the serial version. Okay. So nothing should have changed in this particular case. I should be able to run the Poisson problem exactly as before, and I should get the same result. Okay. Now, instead of assembling, we need to split this range. Sorry, I don't have a voice anymore. So there is a split range function, which is called inside this, that allows us to do exactly the type of things that we need. So I will call this before the assemble system on range. And I will do the following thing. For first of all, I ask how many threads I have. So I do n threads equal And now I am creating a new task group. Thread group. So if you look at this, what this is doing, I want to create an object of a collection of threads that is called on functions that return void. I'm sorry. And now what I'm doing here is I'm creating a set of ranges that uses defender begin active and defender end. And then I loop over all threads. And I add to the group a new thread. That's a Lambda function that simply calls assemble system range using ranges I begin and ranges I end. I think it might not be begin end. I think it's going to be first and second. If I recall correctly. Is it clear what I'm doing? Is it? Sorry, I have to go and drink. Just 1 second. Sorry, it should be better now. Okay, so what I'm doing here is I am splitting the ranges. This function here threads a split range, which we can now copy and search for in DL2. Is returning a pair of forward iterators. And it splits the iterators from begin end into end intervals. And here I'm using split range into end threads. Once I split it into end threads, what I'm doing is I'm basically asking to each thread to call the function assemble system and ranges. Okay. Of course, if the number of threads is equal to 1, this is absolutely unnecessary. And of course, if I use I should use I. And since it doesn't know how to extract information about the type name, let's take that. And explicitly say to display range what type of iterator it has to work. Okay, so now let's keep in mind what we had as a CPU time was 172 and wall clock time was 172, and we were spending 76, 0.76 seconds on this. And we should be able to obtain the same thing with a number of threads equal to 1 that is written here. So if we now run the same thing, I have a segmentation fault. Oh, of course. Let me check. This is exactly a type of example that we had here. And this is one thing that you will learn very quickly. Parallel computing is always difficult to debug and always difficult to understand. So this doesn't seem to be working. And I think it's related to the fact that the end Dolph handler, it's not exactly the same as it's not the same type of begin active Dolph handler. Let me just try with 2 for a second. Then it's a different arrow, which is guy. So I have an issue with this. And I think I have to change the perspective. So in principle, this should work. And I think the reason why it's not working is because you cannot compare this object when you copy it. I think this is not copyable. And this may be an issue on this point because of this. Let me I think the way to do that is the identity. let me postpone this for later. I think the main issue here is that this split range doesn't work for complex iterators like the one that we have in the cells. I remember this used to work, but I haven't been using this for a while, so it may not be the correct way to proceed in this particular case. So, as an exercise, try to make this work using and try to understand why this is actually giving us problems. Before we go forward, I wanted to do the last part, which was to transform this into something that contains scratch data and copy data. Okay. So in order for this to be possible, I will be using objects that are already present in the DL2 library. And I will be creating a assemble system on one cell object, which needs to take as input three objects: the cell, the scratch data, and the copy data. So I will be using Workstream namespaces, which is this guy over here. Mesh worker namespace. And in the mesh worker namespace, there's a scratch data and a copy data, which are objects that basically can be used as a drop-in replacement for scratch data and copy data whenever you have Workstream classes that you need to run. Okay, so let me show you how this works. So the idea now is the following. I want to create a function that I will call so these two guys here, Poisson H. I need them here. And I will create a function which is assemble system one cell. And this takes as input the scratch data and scratch and copy data and copy and a type name of handler dim accusa iterator. So this is a signature of the assemble system on one cell, and copy one cell only need to have the copy data. And it doesn't change that. So this is a const copy data. Okay. So I basically want to rewrite the code that is written in the Poisson assemble on range. Which is this. And all of the guys that are written here, I want them to be outsourced onto the assemble one cell. So let me show you what I mean with this. So I will create this guy here. And then the same thing, which was copy one cell, which only need the const copy data. Okay. And in the copy data that I want to use is this object over here, And it's a template object with a number of matrices, number of vectors, number of indices. This object contains a full matrix, a vector of matrices, a vector of vectors, and a vector of local love indices. And I will be using this object as our scratch data and copy data. So here I using copy data, mesh worker copy data with 111. So I want to use one matrix, one vector, and one set of indices. Of course, if you need to assemble more matrices in parallel, you will want to use both of those guys. And scratch data instead is going to be scratch data here. And if you look at the way scratch data is defined, it's a object which is templated on the dimension dim and on the dimension space dim. Okay, so I'm making this templated on dim, and space dim is by default the other one. Okay. So these two guys are the guys that we are going to be using for our assembly. And now we take a look at the way this scratch data is initialized. So this scratch data is initialized with the constructor of this guy. It's exactly the same as the constructor that you would have for the finite element values. So FE values and scratch data. This is a drop-in replacement for copyable FE values and many other things if you need to, for example, integrate faces. Okay, so here, let's take a look at the assemble one cell. The assemble one cell function should basically have all of these initialization here will be relegated to the scratch data initialization. And so the assemble system one cell will simply set the copy matrix 0 set to 0. So we set the 0 matrix and vector. So this is the copy data content. So the copy data contains a accessible vectors and matrices and local indices. So this will be matrices, vectors, and local indices 0. We want to have cell get dof indices. We want to initialize this with that. Okay, so here I'm basically doing what you see here. So matrix equals 0 as the right hand side equals 0. And we want to call FE values Readme itself. And this can be done by simply calling scratch Readme itself. So this makes sure that you can actually refer to the FE values that is used in the scratch function to as FE values, which is written here. And you can see that by looking at the constructor by the members of the scratch data. So the members of the scratch data allows you to re-init using the cell and returns to you FE values exactly as you would have, as if you had called FE values rate itself. So now I can just copy paste exactly the code that I had here for a single cell. So this is this guy over here. And in order not to change anything, I will just copy all of this. So as you see, nothing has changed. I'm just using the FE values that is inside the scratch data over here. And what I want to make sure is that I make outer cell matrix and equal copy matrix 0, and outer cell right hand side equal copy vectors. Copy vector 0. So that I can actually do the same thing that I was doing before, with the exception of the scratch data. Okay. So here I don't change anything. I just use the same name as before. And here I've created 2 references to those guys. Now, if the cell is at the boundary, what I need to do here is I need to do exactly the same thing that we had before. And so instead of doing it using FE face values, what I do is I do outer and FE face values equal scratch Readme cell F. And this will provide me an object which is an FE face values object initialized with the correct values I had before, that I will have had used afterwards. So as soon as I finished with this loop, a copy data will contain local matrices and local vectors with the correct things in there. And the cell and the assemble system one cell will have used scratch data instead of FE values as we were doing before. Okay. And now I want to construct the copy one cell. So the copy one cell basically is this. But we already have the of indices. So copy one cell, we call constraint distribute local to global. And this is now copy matrices 0, copy vectors 0, and copy local of indices. If I recall correctly, it's called local of indices 0. And I assemble this in system matrix and system right hand side. I don't need a mutex because this is guaranteed to work in serial. Okay. Questions so far? I guess you have many, but I'll finish this right away. So assemble system on range. Now, in order to make it work as we would have expected, I need to create an object, which is the scratch data object. So the scratch data, we call it scratch, and we initialize it with the mapping, with the FE, with the quadrature formula. And then this also requires the phase quadrature formula and the update values. So basically, it's a copy of this, and it's a replacement for all of these guys. Okay, so the scratch object now is equivalent to having multiple copies of FE values and FE phase values. And now the copy data is equivalent to having multiple copies of this guy. And the copy data needs to be initialized when I call it as a constructor with the size. So the size here is FE and pulse per cell. So this will initialize the copy data objects, all of the matrices and vectors that you have there with the copy data objects. Okay, so this should be still working, at least in the serial case. So if I loop from the beginning and from the end, Now, instead of doing that, what I will do is I will simply eliminate all of these guys and call assemble one cell, assemble system one cell, passing the cell, a scratch, and a copy. And then I will remove this, except for the mutex, to make this work with the serial case. This should be copy system, copy one cell, copy data. Okay. Is it clear what I did? I basically moved everything out and put it into the assemble system one cell function and copy one cell. And I'm assembling the mutex. I'm using the mutex here because I would like to be able to run this in parallel. And the scratch data here needs a comma. Quadrature formulas at the end. Face quadrature formulas. Okay, so this now has worked, and this should give you the same result that it was giving you before when we call this on the assemble system globally. When we call this from beginning end. Okay, now this is not going to work for the same reason as before, because we just changed the assemble system range, and this is what was not working. So here, now to make this work using Workstream, so assemble system using, I will call this assemble system using ranges, and I'll create the assemble system separately. And so the assemble system separately will use the following. We'll basically use Workstream run on dot handler begin active, dot handler end. And now we want to pass this class, and this class we want to pass the address of Poisson. And Poisson dim copy one cell and a scratch data that is the same as the one that we constructed before. Which are this? So we create these two guys in the assemble system. And then we pass scratch and copy. And we leave everything else as default. So if you look at the documentation of Workstream run, basically this is equivalent to what we wrote as the assemble system using ranges. Let me just comment this out and call assemble system range dot handler begin active and the handler and so this is what we had before. This works in serial, and here we are doing exactly the same thing, but we are letting the Workstream do the things by scheduling as many assemble system one cell and as many copy one cell as required. Okay. I wanted to compare this with that. I will not be able to do this, so I will just do this with the Workstream class. So there's a version of this, one that takes iterators like begin, active, end. And so you could pass to this using ranges. I don't have that in the Poisson Test. So I'll have that. Now we do. So the Poisson.tc will call this Workstream run. Of course, I have to include the Workstream. Oops, Workstream. Okay. So to summarize, what I've been showing you is the fact that you can assemble the system exactly as you were doing before by splitting the expensive operations onto a function that is called assemble system oneself. You can call it whatever you want. And this assemble system uses scratch objects, which are these guys over here, and copy objects, which are these guys over here. And it uses one of those guys for each one of the tasks that is running in parallel. So not as many as there are cells, but as many as there are parallel tasks being executed. And then it reuses those among all the cells whenever it runs things in parallel. So let's see if this actually works. Okay, so let's take a look at the number of threads that we're using here. Now we're using 2 threads, and let's try to experiment with one first. So with 1 thread and number of Raman cycles, we set 6 and see a reference result. Okay, so the reference result here in serial is 6.76 seconds for wall clock time. And assembly is 49%, about 50%. Now we change the test and we set number of threads to be equal to -1. And we expect this number to go much faster. So it's not much faster, but it is faster. So of course, you have to be careful here. You have to compare apples with apples. So here, this is 3.3 seconds, and this is 0.5 seconds. So I went from 8 to a 1/7 of the original time, basically. So this is, I have 8 cores, and they are enabled with multi-threaded. So you're seeing a speed up in the only thing that we have made parallel of about 7 times, which is close to optimal. So optimal would be 8 times. You would see a better speed up, of course, if you have objects that run with much larger computational time. So if you have this number to be, for example, 20 seconds or 30 seconds or an hour, then this would have a much closer to optimal speed up. For these small times, fluctuations are very small. Okay, so let me stop here, and I'm ready to take any questions. And I'm sorry for being slightly late. I had problems with my voice. Hopefully, stop this.